Good. So what we're going to talk about in this class generically, meaning over the semester, is what I would describe as induction. And by induction, I mean we start with some information about the world, we see some data in the world, and then we combine those things to make predictions. We're going to see that again and again. That, in some sense, that's the heart of machine learning. It's induction. Induction is kind of an interesting thing. So who got a chance to, Coco, I think you put up readings, right? Who got a chance to look at some of the readings? Anybody get a chance to look at some of the readings? I strongly encourage you, this book is free online. I strongly encourage you to look at chapter 2 of this book. We will cover a lot of the material in that chapter, probably mostly next time, although a bunch of the discussion in chapter 2 is in fact about induction as a technique. And in fact, the book makes the argument's been made quite a few times, that there is a reason why probability theory, particularly Bayesian probability theory, is correct for the purposes of induction, that it is, in some normative sense, the right thing to do, right? That you should combine priors, so we'll talk about combining prior information and data in what we call inference, and that gives us new predictions. Okay, that's kind of the heart of chapter 2. The other parts of chapter 2 is how many people would consider themselves familiar with information theory? Stephen? Okay, good. Gokul apparently on a good day. Okay, a handful of other folks have some familiarity. All right, then I really strongly encourage you to read chapter 2, and we'll spend most of next class going over the kind of crash course in information theory, because it turns out that a bunch of those concepts are going to come up again and again in algorithms. So we're going to have to understand concepts like relative entropy, Kale divergence, regularization, and how those relate. So that will be the focus of next lecture. The next kind of background question, how many people feel comfortable with convex optimization? A few more. Stephen does not, apparently.
Oh, yeah.
We can have a separate tutorial if you'd like, Stephen.
Put instructor first.
Okay, so, right. So if I said, like, what a subgradient is, who would you know what a subgradient is? Okay, a handful of folks. Okay, so I think that demonstrates we'll have to cover that in some detail. We were hopeful that that was background, I think, but it sounds like we will need to cover that. Might need to cover a little of that before information theory.
Yeah.
So, okay, might be a slight change to our order of presentations. Okay, good. So induction, going back to that topic. This is the model, and usually, again, if you read chapter 2 of that book, or E.T. James's book, which I also highly recommend, I think it's called The Logic of Science, Probability, the Logic of Science. It's chapter 2. Similarly, is a case for why you should think of probability theory as uniquely the correct thing to do for induction. Well, interestingly, none of these things, they basically make an argument about, well, this is what you should do or you would be irrational. That's the rough argument. But they don't say anything about how well induction as a strategy works. Okay, so people have questioned induction for a very long time, going back to at least the 18th century, but probably much longer. So Laplace gave an example in one of his books on probability theory of the following setup. You see the sun rise for 1,000 straight days, right? So day comes, sun rises, day comes, sun rises. You can ask what it would mean for the day to come in the 17th century without the sun rising. I'm not sure, but humor me. So for 1,000 straight days, the sun rises. What should you predict on the 1,001st day? What might you predict? You're allowed to predict anything you want. Go ahead.
Sunrise.
Okay, good. Sun rises. Why do you predict that?
I would answer.
No good answer. Okay, right. So,
I'd say because it did the previous 1,000 days, but I think that's the answer.
you're doing induction?
Yeah, that's the answer.
Right. It happened before. Maybe it's reasonable to expect it to happen again. Laplace actually gives you a formula for what probability you should assign given that data to the sun rising or not rising. Okay, so there is, which is kind of interesting, right? He can give you a formula to tell you what's the probability the sun is going to rise at that point. Okay, so there was perhaps naturally a critique of this, right? And so the critique is most famously from David Hume. This will, by the way, be by far the most philosophical lecture in this entire class, but I think it's worth thinking about because I think it informs a lot of the algorithms we're going to come up with. Okay, and so Hume's critique was, oh, actually, there's no reason to believe that's true, right? And in fact, imagine you were instead a slight variant on the same problem. You were a chicken in a farmhouse, and for 1,000 straight days, in the morning, the farmer came and fed you. Right? Very possible on the 1,001st day, he is going to come and make you into chicken dinner. Right? But that is not what is in fact going to happen on the 1,001st day. And you don't have any basis to believe that the 1,001st day is going to be the same as the first 1,000 days. Right? That was the essence of his argument. His whole argument is in fact very skeptical. He goes so far as to deny that there are causes and effects, that there's no such thing as a cause and effect, and argues instead that there are just correlations that happen in time order. And then he moves from there into a set of very circular reasoning, which basically means there are causes and effects. But it doesn't matter. So what can responses to this be? So I think it's very hard to say that Hume is wrong in this sense. It really could be on the 1,001st day. In fact, it might even be quite likely that on the 1,001st day the chicken gets turned into dinner. Right? What are the possible responses to this? Anybody have ideas?
By the way, Drew, would
Yes.
you mind using a darker marker?
I could try. I think the blue one works.
Okay.
I think the blue one works. What are some possible responses to this? To Hume's critique. Why do you need a response at all? I would argue you need a response because all of science is just induction, right? What do? We look at data, we make predictions of the future, right? That's like all we do is induction every day. So I guess option one, is Hume is right, and we should just stop doing this induction thing, right? Like, there's no reason to believe it works. Can't count on it. You can try it if you want, but good luck.
He has the point, but
He has a point. Yeah, he has a point.
this is the best thing we can do. That might be my
The
response.
best thing we can do what?
So reasoning based on previous experience, this is the best thing we can do. But that can be incorrect, but we don't have other ways.
Okay, I kind of like that one. So, so one is Hume is right, and you can accept this and all of the other things actually too. These are not mutually exclusive, but it's the best we got. Not unreasonable, and not an unreasonable way to live your life is the best we got. Science seems to work. We're going to go with that. There's a viewpoint. I wouldn't disagree with that. There's a viewpoint which is sometimes ascribed to Albert Einstein. It's also sometimes called the Goldilocks view, which basically says, well, sure, in principle, Hume's right. It could be that way. However, we happen to live in a world where induction does work, right? There could be worlds in which induction doesn't work. However, it'd be very unlikely that there would be intelligent life in universes where induction didn't work because there would be no reason to be intelligent, right? That would not evolve as a strategy because if you can't predict from the future, what's the point in learning anything from the past, right? And so this is the anthropic principle at work. The very fact that you exist is because induction must work. Okay, very fact intelligent beings exist is that induction must work. There's something somewhat unsettling about this viewpoint, though, right? Which is like, it seems like you can ascribe anything to that, right? The world is the way it is because if it was not that way, you wouldn't be here. It's not the most satisfying. So this is we got lucky. It works. The only good reason is because if it didn't, we wouldn't be here, okay? Then there's the viewpoint which I would call I'll call it the no regret viewpoint. Okay, what this says is that any prediction you make could absolutely be wrong. Hume's right. Any prediction you make could absolutely be wrong. Okay. But we can step up a level and say, are there strategies for prediction, for induction, that are the best we could hope for? Okay. So it's not that induction always works, but that if we're lucky, if there are things that we can learn, that certain strategies will turn out to be the best, and that if we follow those strategies, we will do well. Okay, it's a little like the kind of chapter 2 argument, the sort of Bayesian argument. It's the right thing to do. But what we're actually going to do is formalize that. We're going to formalize this viewpoint, and this is kind of a distinctly late 20th century viewpoint that rose out of game theory, also statistics. So late 20th century viewpoint. Okay, and so this is the point we're going to take today, and we're going to go through examples of this. Okay, and so what the no regret viewpoint's going to do is it's going to say, I'm going to make no assumptions about the world at all. Okay, we'll see what at all means. We're going to make no assumptions about the world, and then we're going to come up with strategies for prediction, and we're going to show that in some sense those strategies for prediction are good. And in fact, we won't go through this argument, but in fact there are none that are better. Okay, that's the kind of sequence. Notably, we're not going to assume, for instance, probabilistic reasoning, right? We're not going to assume probabilities on things. That's going to be the kind of key viewpoint of this. Okay, so let's set that up. This, when you try to formalize this, it's often formalized as the idea of prediction with expert advice. Okay. Okay. What does this mean? This means there's going to be a whole bunch of experts. Okay, so think of it in your head as there's like 10 experts, and they're going to make predictions. And let's make the problem really easy to start with, and that there's only 2 predictions you can make, which is, do you get fed or do you go into the pot, right? So maybe slightly morbid. You can choose another example like sunrise or sunset if you prefer. It's fine. And in fact, since it's just a binary prediction problem, I'll probably just be lazy and mostly call it 0 or 1. Right? But in your head, these are predictions about what's going to happen in the world, right? So, you know, you're going to get fed or you're going to go in the pot. Okay. Every expert, it's going to be a whole set of experts, are going to output predictions. So I might index those experts, E0, E1, E2, E3, are going to make a series of predictions. Okay. What are examples? What could an expert predict? Well, we're going to do this over time, by the way. Like every new day in this, you know, the farmer comes out, we're going to make a prediction. Okay. What could the experts predict? Their output space is only 0 or 1. Okay. What's an example expert?
All zeros.
All zeros. I'm going to call that E0 to be convenient.
Yes.
All right. So this expert, pretty dull. All zeros. Okay. I'll also pick expert 1, fill 1. I'll fill that one in for you. Good. What are other things that could be experts?
You saw the previous day.
Good. Yep. Right. So this is like an algorithm which is repeat what happened yesterday. Predict what happened yesterday. That's a pretty good one. Good. What about one that was trying to be adversarial, trying to trick us? What might it do? It could. It could do something, right? It could do something like 0, 1, 0, 1, so on and so forth. It could do something like imagine that you get fed every day. It could, for a long time, say 0, 0, 0, 0, 0, 0, 0, and then when you think it's the right expert, start saying 1, 1, 1, 1, 1, 1, 1, right? So could be out to get you. So, 0, 0, and then it suddenly starts outputting 1. Just when you're confident that this is a pretty good expert, at least if you get fed repeatedly. Okay, those are all example experts. we're going to have a notion of a loss function. I'm going to start out with the simplest loss function, which is something's going to happen in the world each day. Maybe we call that y, right? Y0. Sorry, y. The index 0 is only going to index time. And y, something's actually going to happen. So maybe 0, 0, 0, 1, 0, 0, 0. Okay. And this is not preordained. Okay. I'm writing it as a sequence right now, but you shouldn't think of it as a sequence that's preordained right now. Okay. You should think of it as at every time step, the world is going to make a choice of 0 or 1. Okay. And after you will make a prediction. That's what you're going to do. The world is going to make a realization of what happens. Its realization of what happens could depend on the entire past of what has happened. It's not probabilistic. You don't need to think of anything like that. In fact, again, it could also be out to get you. It could be trying to trick you. Okay? And then it will output a number, and then you're going to pay a loss. Okay? So we're going to have a notion of loss t. Okay? For the sake of the first part of this, I want you to think of the loss as just binary 0, 1 loss. You either get the prediction right, in which case you pay 0, or you get the prediction wrong, in which case you pay 1. Okay? So loss t is going to take a prediction. I'll call that p for now. P might be a bad choice of outputs. I don't know. And y. And it's either going to give me a 0 or a 1. Okay. So what are natural things you could hope for? Well, the thing you would like to be true, right, is that you get a loss of 0. Your algorithm gets a loss of 0. Okay, that's going to be really hard, right? You got to get all your predictions right. Probably too much. Okay, you could hope that sum over t over time steps, maybe up to, I'll use capital T to denote the kind of final time step. Okay, t is going to go from 1 to t. You could hope that this, on average, goes to 0. That turns out to be a lot to ask, too. Imagine that the expert advice you are given just isn't very good, right? Like, in fact, imagine it was just these two experts, and the output that happened was actually interesting, right? It wasn't just the sequence 0, 0, 0, 0, 0. It's really hard to expect this to be true. It's kind of what we wish were true, and I'll harken back to this in a minute. Okay, so that's the setup. The weaker thing I could ask, okay, and that I actually can do a good job of, is say, I want to do nearly as well as the best expert if I knew what the best expert was in advance. Okay, if I could cheat and know what the best expert was, I want to do nearly as well as that. Okay, which, at least when you first think about it, sounds sort of magical. Okay, but what does that mean? I want sum of the losses of my predictions at time t. Okay, I'm gonna drop the dependence on y and just think about it as it's buried in the loss function at time t. Okay, time t minus the loss at the prediction at time t of E star, the best expert. Okay, I want this, at least on average, to go to 0. That's what I mean by nearly as well as the best expert. As time gets longer and longer, I'm getting closer and closer to doing as well as the best expert. Okay? And again, this quantity right here says I get to pick any expert I want. For any expert here, I'm going to do nearly as well as that expert. Does that make sense as a requirement? Okay. What are thoughts on how to achieve this? If you know how to achieve this, don't answer. If you don't know how to achieve this, I want your thoughts on how to achieve this. How could I get this? So this property, by the way, this quantity right here is called the regret. If you put the 1 over t, it's the average regret. Okay? These algorithms that achieve this are going to be called no regret. They should actually be called no average regret, right? Because it's not that the regret is going to 0, it's the average regret is going to 0. It's going to be called no regret algorithms. What's a very natural thing to do? What's the most natural thing to do? You got a bunch of expert predictions. It's time step 10. What should you do?
You look at the history and pick the expert that had least amount of regrets.
Yeah.
I guess E0 right now.
Right. So the most natural algorithm of all, I think, is sometimes called follow the leader. Okay. And it does exactly what you just said, right? The obvious thing to do is I'm just going to look at the history of predictions. I'm going to look at which expert has the lowest loss right now, right, over the last whatever t time steps, and I'm just going to predict whatever that expert says. Okay, this sounds like a good idea. It's actually almost a good idea, right? And in fact, I think Stephen's going to talk about how to make it a good idea at some point, but it's slightly busted. And let's see if I can convince you that it's slightly busted. Imagine you only have the two experts, E0 and E1. That's the only two you got, okay? And meaning expert 0 is going to always predict 0, expert 1 is always going to predict 1, okay? And you want to compete with them, okay? And imagine, we have to have some kind of tie break, right? Because like at the very beginning of time, there's no expert is better, okay? So it doesn't matter how you can tie break, you can break any way to tie break, but let's just pick one for the sake of discussion. I'm going to tie break and always choose E0. I'm going to lexically order them, and if both experts are doing equally well, I'm always going to pick E0. Okay, good. So what's going to happen? E0 is going to unsurprisingly predict 0, right? It has, let's do E0 correct, E1 correct. Okay, our prediction P, and what happens in the world? Y. Okay, so no correct in the first time step because we haven't seen anything yet. What do we make our prediction? What's our first prediction? Given the tiebreak rule I gave you. 0. Good, I'm going to predict 0. Okay, the world does not like me, and it predicts 1, and it says 1. I pay a loss of 1. Good, who's right at the next time step? E0 has 1 correct. No, sorry, E1 has 1 correct, right? E0 has 0 correct. What am I going to pick? I'm going to predict 1. Okay, the world is very annoying, and it says 0. Okay. Now what happens? E1 is correct once, E0 is correct once. What am I going to pick? E0. Good. Guess what the world does? It's going to predict 1. It's going to make 1 its output, the real state of the world. Okay. What is happening in this instance? Am I doing nearly as well as the best expert? I'm always wrong, right? If we keep doing this, my predictions are 100% of the time wrong. Okay? So in fact, my regret is OT. Right? In fact, it's as big as it could be. Every time step when we do this, I always make the wrong prediction. And I will always make the wrong prediction for as long as we run this. Okay? If the world is out to get me, as the world is clearly out to get me. Okay. What else might you do? What are other things you might do? We'll revisit this because we can fix it later. Okay. The basic problem is it's overfitting. That's the basic issue. It's way too unstable, and it just jumps between solutions, and it can get tricked. Okay. So the world puts it on a knife's edge and then tricks it. It's basically the same phenomenon as overfitting. What else could I do? There's an algorithm. This algorithm is adaptive, which is cool. It's at least trying to see which experts are good. There's a non-adaptive algorithm, which is I could always just take the majority vote, right? I could say the majority of experts, what do they say about the world? And output with what they say. That seems like a strategy. What's good about that strategy? It's super stable. It's not going to get tricked by this kind of problem, right? What's bad about that strategy?
What if your experts do like worse than 50%?
Yeah, what if there's a whole bunch of experts that are bad, right? You'd love to figure out, hey, those experts are bad, and stop paying attention to those, and start paying attention to the ones that are doing well. And this majority vote never does that because it doesn't learn at all from the data. Okay, so fault leader was attempt 1. Attempt 2 was majority vote. Okay, they kind of fail in complementary ways, which is what we're going to take advantage of in a moment. Okay, now I'm going to simplify the problem for just a little bit to suggest an algorithm, and then we're going to go back to the original problem. I'm going to add one additional piece of information. Let's just assume for a moment, and then we will fix it, that there is one expert, I don't know which one, but there's one expert whose loss is 0. Okay, so assume for a moment that L of E star sum over T equals 0, right? It always gets the right answer, okay? So we might call it realizability, something like that. There's always an expert that gets the right answer. All right, let me suggest a simple algorithm. I think this is often called the halving algorithm. Okay, what I'm going to do is I am going to look at what all the experts predict, and I'm going to look at, are there more experts who predict 0, or are there more experts who predict 1? Okay? If there are more experts, and we need some tie break, right? So if the sum of, we'll just call it the number of experts. The number of experts such that EI equals 1 is greater than or equal to number of experts so that EI equals 0, then I'm going to output 1. Else, I'm going to output 0. Again, I have to tie break in some way, right? Okay. Now I run this algorithm, okay, where I do these predictions, except I'm going to add one thing. I'm going to adapt, which is if an expert ever makes a mistake, I'm going to remove it from consideration. Okay, so every expert that makes a mistake, I remove from consideration. Okay, how many mistakes can I make if I do this? Total mistakes, which is exactly the same as total regret in this sense. Not average regret, total regret. How many mistakes can I make? I heard there are lots of answers that sound right. Is it better than that, maybe? Better than that, even? What happens if I make a mistake? What has to be true for me to make a mistake? Over half of them are wrong, right? Over half of the experts had to have output the wrong thing, or I wouldn't have output the wrong answer. Okay, so over half the remaining experts have to be wrong. Okay, and what happens to those experts? They're taken out. So how many experts, for every mistake I make, what happens to the number of experts? It's halved, okay? There's one expert who's correct. How many times can I have? Not n times. Log base 2n, right? Log base 2n, probably with a ceiling. I'll ignore the details of the +1s or -1s. That's my regret, okay? So this is kind of cool, right? Because I can have a huge number of experts and make a tiny number of mistakes as long as one of my experts is correct, right? I can have like exponentially large set of experts. It's not computationally efficient, right? I mean, you'd have to think about it for special cases because I have to keep track of the experts and I have to check them all. But I'm going to make a tiny number of mistakes while doing as well as that best expert. Okay. The annoying part of this is it's not robust to noise, right? Because now imagine that there's experts that make small numbers of errors, but not 0, right? The problem is I killed them. Right? As soon as they made a mistake, they're out, right? Okay. A way to think about this algorithm I just described is that I have a weight on each expert, and that weight starts at 1, okay? And then what happens if the expert gets the answer wrong is that I set its weight to 0. I multiply it by 0 and it goes away. Okay? And so what I'm actually computing is the weighted average, or the weighted majority, hence the phrase weighted majority, of my experts. Okay? So I'm taking their weights, multiplying it by their prediction, and deciding which of these two things is bigger, and then I'm going to output whichever one is bigger. Okay? That's my strategy. Does it make sense? Okay. So basically, if some of the fancier version of this, so this is going to be called the deterministic weighted majority algorithm. First, I'm just going to rephrase the old algorithm, and I'm going to say, I'm going to sum the weights on expert I such that EI is predicting 1 at a given time step, and I'm going to compare that to the sum of the weights I so that EI is predicting 0. Okay? Does that make sense? What I'm trying to say in very questionable math, right? Look at all the experts who predict 1, sum their weights. Look at all the experts that predict 0, sum their weights. If this is greater than this, output 1, else 0. Okay. Okay. And now the algorithm before was, if the expert is wrong, multiply its weight by 0, right? So the old algorithm is weight I, expert I, at t plus 1 equals weight I at t times 0 if mistake. If mistake for expert I. Okay. So what I said is this thing's too aggressive because if your expert makes any mistakes, it's gone. How might I soften this?
Instead of multiplying 0, multiply by a different number that's between 0 and 1.
Yeah. Let's go with a half. There's nothing special about a half. It's just convenient. Okay. In fact, we'll talk later about how you can set this number to be optimal. Okay. Good. So I'm going to make it a half. Okay. Now I'm going to claim that this algorithm is more robust than that halving algorithm, but has some similar properties. And let's see if we can analyze it, if I can remember how we analyze it. Okay. The trick here is what we were keeping track of before what were we keeping track of before to do the analysis when we claimed that there was log base 2 n mistakes? We were keeping track of what? The number of experts who remaining, right, that haven't been eliminated, right? Equivalently, if we're following this rule, I was keeping track of the total weight. That's the thing I was keeping track of, right? Because the weights were either 1 or 0, and then if I'm keeping track of the number of experts remaining, I'm just keeping track of the total weight, right? Okay, so let's look at the total weight. Let's look at the total weight. I'm going to call that capital W. Okay. Total weight. The total weight is lower bounded by, well, what's it lower bounded by? Weight's got to be at least, the total number weight has to be at least how big? Is there anything that bounds how big it can be? I'm sorry? The weight of any given expert. Good. What is the biggest such weight?
Weight of the best expert.
Weight of the best expert. Good. What's the weight of the best expert at a given time step?
The number of mistakes.
The number of mistakes. The number of mistakes. Exactly. So there's going to be some expert, E star, okay, that's made the least mistakes. That can change, which is E star, can be different at each round, right? So E star is not a fixed thing, okay? This weight's got to be at least 1/2 to the M star, okay? It's at least that big, right? It could be a lot bigger, right? But there's at least one expert. It made the minimum number of mistakes, okay? It's at least as big as 1/2 M star. Okay. Can we put a bound on the other side? This is going to be attractive because we're going to want to bound our performance in terms of M star. Okay. Can you tell me a upper bound on the weights? Before, we had an upper bound on the number of experts that were remaining in terms of their number of mistakes, right? Because in terms of the algorithm's mistake, right? Because every time the algorithm made a mistake, the number of experts got halved, right? What happens here? What happens to the total weight every time I make a mistake? Every time my prediction is a mistake, what happens? What has to be true to make a mistake?
You lose at least 1/4 of the total weight.
Right. Why?
Because you you multiply at least half of your total weight by 1/2.
Right. So half of the weight of the experts had to be wrong for me to make a mistake. For those experts that are wrong, I reduce their weight by 1/2. Right? So what that says is my weight starts out as n, the total number of experts, okay? And it goes down by 1/4, right? Which means it's 3/4 to the m, right? Or m is the number of mistakes the algorithm makes. M star is the number of mistakes the best expert makes. M is the number of mistakes the algorithm makes, the predictor makes. Okay? Does that make sense? Okay. Now we do some algebra. Okay. So this is 2 to the minus, 2 to the minus m star. And this is, again, I can chain together the less than or equals, right? And just ignore the total weight. Good. Is, I'm going to take log base 2 of both sides. Base 2, log base 2. Okay, this is minus m star. Good. This is log base 2 of n. That's cool because we had a log base 2 of n before in our total regret. But I got an extra term, right? And this is log base 2 of 3/4 to the m. And so I'm going to pull that down and put my n here, right? And then I'm going to get what? M log base 2 of 3/4. Oops, that's a plus. I'm going to make that a minus because I want it to have the same sign as this thing by just flipping this. Minus log 4/3. Okay, now I'm just going to rearrange. And that means that capital M, just flip sides, is going to be less than or equal to m star plus log base 2 of n times a constant. And that constant is going to be 1 over log base 2 of 4/3. As everyone knows, that's about 2.41, of course, right? And that's my bound. Okay, so the total number of mistakes that this weighted majority algorithm will make is upper bounded by the mistakes of the best expert plus a term which is basically telling us how quickly we can find the best expert, right? So if there's a lot of them, it's going to take us longer, right? But the cool part is it's a logarithmic dependence on the number of experts. Okay, does that make sense? Times 2.41. This algorithm is not no regret. Why not? What did no regret mean? it has a regret bound, we just computed it. Why is it not no regret?
This made up number 2.41 is too big.
Fundamental constant of the universe, Stephen, but okay. Right, what do I want it to go to be no regret?
Log 2 of it.
What's that?
Log base 2 of it.
Well, I need it ultimately that this thing is not growing linearly in the number of mistakes of the best expert, right? I need it, well, it is going to grow linearly in the number of mistakes of the best expert. I need it to not be 2.41. I need it to go to 1, right? I can't actually do that with this algorithm, it turns out, for 2 reasons, a dumb one and a not dumb one. The dumb one is that 1/2 was an arbitrary selection, right? We could have picked a different number. What happens, do you think, intuitively what happens if you make this number closer to 1? Yeah. Yeah, you get the algorithm, right, take it to 1, it just ignores the data entirely, right? And it's super stable, right? But it's super stable, right? But it doesn't actually achieve no regret, right? If you get, basically you're learning slower and slower. As you get it closer to 1, you're learning slower and slower, okay? That's actually what we're gonna wanna do. We're gonna wanna tune this number so that if our time horizon is really long, we are less responsive, and if our time horizon is really short, we wanna be more responsive. And in fact, what will happen ultimately is we'll adaptively tune it. We'll make the learning slower and slower and slower as time goes on, okay? That's actually what we're gonna do. The other reason this turns out can't be no regret, and that we actually can't achieve no regret with this algorithm, is we're actually gonna need to randomize, okay? That's the subtle point. And so I'll take you through the randomized weighted majority algorithm next. Okay, let's do the simplest version, and then we'll do the complicated version. How are we doing on time? Doing okay. What time are we done, Stephen?
12:20?
12:20? Okay. Okay, so let's do the randomized weighted majority version 1.
Trude, I think there's a question.
Sorry? Yeah, please.
To prove it's not a no regret algorithm, don't we need a lower bound on M as well?
We would, and the answer is we can construct a lower bound by showing an example where this is tight. Yep, we can show examples where this is tight. I actually think the example we gave before, this kind of oscillating one, actually is tight for this problem, I think. And so you are correct, an upper bound does not prove that it's no regret, but it turns out that that is basically tight. Good. Randomized weighted majority. Okay, randomized weighted majority. What we're going to do is we're going to choose an expert in proportion to WI. Okay, meaning what I'm going to do is I'm going to assign a probability of I is weight I over sum over J of weight J for all the experts. Okay? And then I'm going to pick that expert, and whatever it predicts, I'm going to predict. Okay? Predict what that expert predicts. Okay, good. Good, and then I'm going to do the same thing. I'm going to update my weights. Weight I, t plus 1 is weight I, t times beta, if the prediction is wrong, for some beta. And again, you're thinking of beta between 0 and 1. Okay, that's my prediction. That's my regret. There's a thing that's very cool about this version of the algorithm that's not immediately obvious. Anybody? A subtle, see if you can figure out. If I'm choosing an expert in proportion to WI, notice I'm no longer combining their predictions together, right? Before, what I was doing is I was looking at all the experts that output 1, right? And I had to aggregate them together as a group, okay? This algorithm, as I described it, just picks an expert in proportion to its weight, okay? This is if wrong. Okay, good. This one just predicts an expert in proportion to its weight. It doesn't actually matter anymore that we think of this thing as predicting zeros and ones. The experts could now predict anything at all. Okay? They could predict trees, right? Like they could predict some kind of structured complex object. They could predict an entire sentence, right? All that matters is I can choose in proportion to a weight on that expert, and then I can answer the question, was the expert correct or not? That's all I need to do for this algorithm anymore. I no longer need to like aggregate together all the ones who predict 1 and all the ones who predict 0, okay? So the experts can now predict really complicated things, anything I like at all, as long as I can measure the loss of that expert. Okay, so let's see. I'll give the thing we have to do now, though, is we now can't easily bound the number of mistakes directly. Why can't we bound the number of mistakes directly? It's stochastic, right. This algorithm is picking an expert in proportion to weights. So what could I bound? I could bound the average, right? I could look at the expected regret of that expert. Okay, so the expected regret of this, and I won't spend much time on this because we're going to go to the fancier algorithm in a moment. So the expected number of mistakes is less than or equal to m star. Natural log 1 over beta plus log n over 1 minus beta. Again, I'm not going to spend any time on that because the fancier still version is more general and the analysis is simpler. So we'll do that one. Okay, now we're going to go to the general weighted majority algorithm. Stephen may do a variant of this. I'm not sure exactly what Stephen's going to use in this, but I'll give you the version that I'm going to use. So same thing. We're going to set all the weights to 1. That's the initialization of this procedure. I skipped the initialization. Initialize all weights to 1. Okay. I am going to predict the experts in proportion to their weights. Okay, now I'm going to adjust the weights. And the weights I'm going to adjust are going to be weight I t plus 1 equals weight I times exp of minus epsilon times the loss of expert I at time step t. Okay? Before, this loss was just 0 or 1, right? You either got the answer right or you got the answer wrong. Okay, this version, we've now generalized 2 things, right? We said, hey, we can now pick experts' predictions, and we don't have to say that the predictions are 0 or 1. They could be anything, okay? And the second thing we generalized is this can be any loss function, and I want you to think of this loss function as now between 0 and 1 continuous numbers, okay? Does that make sense? So I can handle a much broader set of loss functions now, right? Continuous loss functions where you can be partly wrong, partly right, et cetera. Okay. And the expected regret of this guy so, because again, we only can talk about expected regret. So what's regret mean again? Remind me. It's not the number of mistakes now. What is it?
The loss compared to the best expert.
The loss compared to the best single expert. Yep. The expected regret of this guy is going to be epsilon times the sum of the losses of EI star, the best expert, plus 1 over epsilon, I think. Yep. Times log, natural log of the number of experts. Okay. So I have a free parameter here, right? Okay. What if I tell you in advance that this problem, we're going to run this problem for capital T time steps. You're going to have to make capital T predictions. Okay. How might you set epsilon? Well, first, how might you set epsilon just to minimize this thing? What would your strategy be?
EMGM inequality. Or differential.
That potentially might work. How might you... What's a good strategy to optimize something? What do I have to set?
Set the derivative with respect to epsilon to 0.
Yep. Okay. I would, however, then need to know the loss of the best expert. Okay. What is the biggest the loss of the best expert could be?
The wrong choice each time.
I'm sorry?
The wrong choice each time. Like if you have no,
I think I'm just not hearing you louder.
if you have no information ahead of the problem, I guess it's just the wrong decision each time step.
So it's T. Yep. Okay. If you go do that analysis right there, you're going to end up with, anybody have a guess? What's epsilon going to be? It's going to depend on log n. Anybody have a guess as to what the form of epsilon is going to be? I want this thing to be sublinear, right? I want it to grow sublinearly. The actual optimum is going to depend on the number of experts. But like roughly, what do you think epsilon should be? In terms of T.
Square root T over ln n.
Around, over what?
Ln n. Or the,
Well, again, I heard 11. I was like, that's an interesting choice. Let's just make it square root T for right now, right? But if you just, you're right, that's what it's going to be, right? But if I just make epsilon equal to square root T, okay, what happens? This term, well, actually 1 over square root T, whoops. Whew. What's going to happen to this term? How big can it be?
Those immediately with the root T.
What's that?
It will be at most root T.
It's going to be at most root T. Yep, good. This term is also going to be what? Root T. Okay, so the whole thing will be no regret. Okay, that is the analysis in a nutshell. You can actually go set the optimal, but you then need to know the number of experts, and ideally you would know the loss of the best expert. That would be kind of a cool thing to actually help you set the optimal rate. Okay, now I want to talk about, very briefly, about some example applications of this. Stephen is going to go through like serious applications of this later. Yeah.
Self-driving cars.
Self-driving cars, yeah.
Is exponent the best choice of function here? As in to get the best, like up to constants, is the choice of exponent there the best, or is there a better one?
EXP,
Yes.
as opposed to some other arbitrary function, or like 2 to the,
Other arbitrary function, or
Yeah.
class of functions.
yeah, so that's a good question. There's a very similar version of this, which might be the one that Stephen is thinking, right, which is like 1 minus epsilon times loss T of I, which behaves very similarly, and the reason it behaves very similarly is like this is the Taylor series expansion of that, right? I actually don't remember which of these is better in theory.
I think one of them will have the quadratic on the right-hand side of the L squared,
Yeah,
L star squared. But you know, in this style of analysis, I don't think it make a difference because you merge everything. You upper bound the first term on the right-hand side by T.
yeah,
So you come out the same bound.
comes out the same bound. I had a vague memory that these came out different when you had positive losses.
Oh, yeah, that might make.
I thought it came out slightly different. So yes, there are other choices besides that one. In fact, there's one that's very common. It might be so common you might just see it later, which is this. But again, this is just the Taylor series expansion of this, so they actually behave very similarly for small epsilons, right? I don't know any other choices for that, but I do know that in the worst case, the best you can do is square root t. So we're actually at the limit of what we can achieve. The best regret we can get is a regret that grows like square root t.
Is there other constants as well? Because I know there's like a log, like root log n constants. Can that be improved or no?
The dependence on log n can definitely not be improved, because even in this kind of extreme case when there's something that has a loss of 0, you can't beat this halving algorithm. Halving algorithm is optimal. You definitely can't beat the log n thing. You can't beat the rough form of square root t. In terms of constants, it's very possible. I don't know the answer in terms of constants.
Don't remember.
Yeah. That answer is known, but not to me. At least I'm pretty sure that answer is known. Good. So in some ways this seems semi-magical, okay? It's because we're doing as well as the best expert in hindsight. Like we get to cheat, right? And say, what was the best expert if I get to see all the data in advance and I'm doing nearly as well as that? You might think it's more magical than it is. So let me try to disabuse you of the more magical than it is, okay? See if I can explain to you what it's not. So let's imagine a problem for a moment where what you got to do is invest in some asset choices, okay? Meaning you could put your money in Walt Disney, you could put Walt Disney stock, meaning you could put your money in real estate, you could put your money in gold, you could put your money in a money market account, right? US Treasuries, whatever. It's a whole bunch of things. I'm going to think of those as experts. Does that make sense? Okay. And what do I want to do now? I want to compete with the best expert in the sense of I want to do nearly as well at making money as if I had known in advance which of those assets was going to be the best performing asset. Okay? That sound like a reasonable strategy? Be pretty cool, right? If I could give you an adaptive strategy that made nearly as much money as if I told you in advance what the best asset to hold was. Okay? That's the claim. Okay. What might a loss function look like for that? Spend a brief bit of time. It's actually like a gain function in this case, right? A very common thing that people like to optimize is like the multiplicative gain in their returns, right? So you start out with some initial capital, whatever, $100, okay? And what you would like to optimize is not the total amount of money you have at the end, but essentially the log of that, okay? Why might that be a thing that you'd like to optimize? It's like the multiplicative return. One, it's mathematically convenient because it will make it so that we're summing over time rather than multiplying over time. So our losses will be of this form, right, that we're summing over time. That's a fine reason for the purposes of this class. But it's worth noting that people, not for mathematical tractability reasons, like that anyway. Why might you like that?
Exponential growth.
Right. So we're talking about maximizing the rate of exponential growth, right? I think also people tend to, there's an example of this called the St. Petersburg paradox. People tend to view something like, let's say you make $20,000, okay? If I make it so you make an extra $20,000 a year, does that make you and a person earning $1 million a year, does that same $20,000 make you equally happy? That's what it would, if you believe that your loss function was like additive wealth, you would think getting $20,000 if you had $20,000 would be equally good as to getting $20,000 if you had $1 million, right? Most people would say it's more like your quality of life changes as you, like, say, double your income, right? If you go from, like, I make $20,000 to $40,000 a year, that's a noticeable change. If I go from 40,000 to 80,000, that's a noticeable change, right? If I go from maybe 1 million to 2 million, that's a noticeable change. But going from 1 million to 1,020,000 is not going to change your life, right? Okay, so typically people take a log as their loss function. So they're looking at the log of the returns or the sum of the logs of individual returns. And that's what you would run weighted majority on. Okay, it really is true that if you run this weighted majority algorithm among different asset classes, you will do nearly as well as the best expert in retrospect. It really is true. People have actually used variants of this to invest money, amazingly enough. Allegedly, Tom Cover and Thomas, excellent book if you guys want an information theory resource besides that one, not free, annoyingly, allegedly made real money doing this. Okay, what are the problems with this? There's two problems with this strategy that I just described, right? What is it? Randomized weighted majority, what it will do is it will end up putting money across multiple assets. It'll tell you what fraction of your wealth to put in each asset, right? And you will have your money go up in proportion to that. But there's two things that's wrong with the strategy. Thing one is in the real world, you pay transaction fees, right? So every time you make a change to your portfolio, you pay some costs, okay? Thing two, and this is the point I want to make about regret, is what regret says is you will do nearly as well as the best expert if the loss functions wouldn't have changed, okay? Right, so what you're saying is on the loss functions, but those loss functions are fixed, right? We're saying sum of LT of our prediction, right? Prediction T minus sum of LT of E star, okay? We're saying this quantity is going to be sublinear, right? Is sublinear. Okay, it's not saying that if you had made a different set of predictions and those had changed the loss functions, that you would be good on those loss functions. Okay, this is sometimes called counterfactual regret, which is what you might like is truly magic. That if you made this set of, if you had made a different set of predictions, right, maybe the same predictions as E star made, you would have done as well as that. Okay, in the finance case, does anybody have an idea of how this arises? How would the set of gains change as a function of your predictions, where you put your money?
Every time decision is a step forward in time, so
Yep.
the world changes. And
Yes. Imagine you make really small investments in very liquid assets. You're not going to change the rate of return of those things, right? If you go buy Disney stock, you will negligibly change the price of Disney stock. And so the gain you get will indeed be the gain you would have gotten. Imagine you make really large investments, right? Like you trade 10% of Disney stock. What happens? Let's say you sell 10% of Disney stock. What will happen to Disney stock? What's that? Price will drop, right? And in particular, what that means is your trades change what the losses would have been, right? You affect what those losses are. Okay, so this actually limits the practical applicability of this algorithm. If you're actually going to change the prices of goods by your buying and selling them, right, then the loss functions will change at each time step. And what you're not getting is this idea of counterfactual regret. You're not getting as good as the best expert had you used the best expert's predictions and those change the loss functions. Does that make sense? It's a really subtle point. I don't know a better example to give than this like move the market one, because it's an example where for very small values, you don't actually change the losses. For big values, you actually change the losses. Okay. Are there questions on this idea of regret? Stephen.
Is one other issue I thought of was, you know, the L you define is the multiplicative
Gain.
changes,
Yep.
gain or
Yep.
so getting a sublinear regret in the multiplicative space
Yep.
could translate still in a rather large gap in terms of absolute money, right?
It could.
Okay.
Yep. The other thing you need is you need the losses to be bounded
I see.
between 0 and 1. That turns out to be equivalent in this particular instance to saying no asset will change price by too much, right? Sometimes called the no junk bond assumption, right? There's no asset you can buy that's going to drop to 0, right? So at any given time step, it will never drop by more than 50%. You're going to need that because otherwise you can't bound the loss function, right? That's the third assumption that's buried in there. And there are indeed assets that sometimes will drop very precipitously, right? So then the loss function can be very, very large. You can always rescale the loss function, of course, but it just changes the scale of the regret. Other questions on this no regret idea? So where we're going to use this, we're going to use this in a bunch of places. We're going to use it for imitation learning. It's going to be the core of our argument for online interactive versions of imitation learning. We're going to show that if you use a particular style of learning interactively, you're guaranteed to get good performance, which is kind of neat. Okay, we're also going to use it in a whole suite of algorithms. Stephen's going to analyze if you play a game with a no regret algorithm, think rock, paper, scissors, right? Imagine you play rock, paper, scissors, okay, versus an adversary, okay? The claim is going to be if you play a no regret algorithm on any such zero-sum game, right, constant sum game, you will end up doing nearly as well as the optimal strategy. If you're playing against a suboptimal expert, you can actually do better than the optimal strategy. That's going to be the thing. And in fact, you can play two regret players against themselves, and in some sense, that Stephen will talk about, they will converge to optimal play. Okay? That's kind of the neat thing about these no regret players. Even in adversarial situations, they give a reasonable answer. That's the thing that's kind of cool about them. And so we're going to use that as the base for a whole series of techniques like inverse reinforcement learning, where we have to solve a game. Okay, and we're going to use no regret learners to solve that game. Okay. Any questions, or we might launch into the joys of convexity for 5 minutes. You should have questions. It's weird. Again, I find it semi-magical. All right.
Can I ask a question?
You can.
How worried should someone be about the expectation here?
Say more.
Like, if the average of the, the expected value of this, okay, I made some money, but
Yep.
50% of the time I end up totally broke. That seems kind of bad.
That never happens in the logarithmic version of this, right? Because that's actually, again, part of the reason for the logarithm, right? Is you're going to end up not putting all your money in one basket, right? It's always going to just go up or down. So you never have the go bust version of this. That doesn't mean that there's not variance, right? There's still variance. How bad can it be? These are independent draws, right? So you're going to have a law of large numbers bound on performance, right? I imagine you're going to get something like a square root of t on the how wide the error can be from the mean, right, as well. So I think it's probably the best you could hope for. Okay. Anybody want to tell me, because we're going to use this next time, anybody want to tell me what a convex set is?
The convex combinations.
What's that?
For every 2 points, the convex combination of the 2 points.
Yeah. So in pictures, if I take A and I take B, all the points on the line between A and B are also in the set. So if A and B are in the set, right? So for all A and B, that A is in some set C, B is in some set C, right? Then what? Convex combination is what? 1 minus alpha times A plus alpha times B is also in the convex set if alpha is what? Uh-huh, good. Okay, that's a convex set. Good. Intuitively, why are convex sets interesting? Do you have an idea? What we're going to do, by the way, is we're going to optimize over these things. That's the ultimate thing we're going to care about. We're going to optimize over constraints that form convex sets.
The gradient points to the global optimum.
I would say that we can do gradient descent without getting out the set.
Yeah, I would say it kind of implies you're never going to get stuck because you can, from every point in the convex set, you can see every other point, meaning there's a straight line to every other point in the convex set. So you never have some weirdness. What's really tough optimization problems is you have some really complicated shape, maybe with like a really narrow passage, and like your current optimization iterate is up here, and the optimum is like over here, and you somehow have to like, you can't see that point, right? You have to like somehow you either have to like leave the set, right, which could be hard because maybe the function's not even defined outside the set, or you have to somehow find your way through some narrow passage. So convex sets are the nicest set in this types of set in the sense that you can see every point from every other point. You can just move directly towards any point in the set. Okay? That's intuitively, at least my view, of why convex sets are particularly interesting for optimization. What's a convex function?
The epigraph of the function,
What's an epigraph?
like everything above,
Okay, good. So I got a function.
is a convex.
Here's my function. Good. I can talk about what's called the epigraph, and that literally means all the points that lie above the function. Okay? So you're picturing this in your head. Okay? All these points. That's our set right here. It goes up to infinity, right? Okay? Notice nothing in my convex set definition said I couldn't go to infinity. Right? That's perfectly fine too. Okay. All the points in this epigraph that epigraph is a convex set itself. Okay? So notably, like if I take a line from a point here to a point here, all those points are also in that convex set. Does that make sense? Which also says this line lies where? I take a straight line between 2 points that lie on the function. What's true about that line?
Always lies above the function.
The line is above the function, or equal to the function, right? Because the linear function is also a convex set. Okay? I'll note there's no requirement that this thing be smooth. Right? Important point, right? It could look like this. That would be a convex set too. Okay? Same property, right? If I look at this point, and this point, and I look at the line between them, that also lies above the function, and that epigraph is convex. Okay? That's definition of convex function. We'll stop there, and we'll do Jensen's inequality, I think, next time. We'll do subgradients and Jensen's inequality next time, I think.